Hello and welcome to my talk at CppCon. My name's John Lakos, and I'm here with my video buddy Kevin Klein. He's the greatest. He's helped me to get everything going, and I'm looking forward to trying to describe to you something that I've been working on for a very, very long time, and hopefully it will be of some value. And so I will move ahead. This is me. This is my new book. This is me with my new book. What we're going to do today is talk about the first chapter, chapter 0, which is an overview of what's really important. The motivation for the entire 3-book series is hierarchical reuse, and everything else is kind of a detail. There are 3 more chapters in this book, Process and Architecture, and there are 2 more volumes planned, and in fact, those volumes were written already, and the 3rd volume was written first. It's kind of like a Star Wars trilogy, and they include design and implementation in volume 2 and verification and testing in volume 3. So let's get started. This may look familiar from a book many years ago, and it's describing the trade-off that you make between product, schedule, and budget. And you can think of them, as J.C. Van Winkle pointed out in the book, as slider switches. You can adjust 2 of them, and then the 3rd one is pretty much dictated. So for example, if you want to build something at a given date and you have a certain budget, then the quality of the product is kind of determined. If you have a certain budget and you can take as long as you want, then you can do things more efficiently, perhaps by linearizing them to get a better quality product. Bottom line is, if you pick any 2 of these, the 3rd one is kind of determined. So the idea here is, what can we do to break out of this triangle? And literally 20 years ago, I was struggling with this problem, and the solution was what we're about to talk about today. So what we want to do is we want to start in 2020, and this original diagram from the book was started in 2000, and the 240 triangle was really 2020, but we actually went through this process. So now I'm taking 20 years of experience doing this, projecting out another 20 years to show that the more we do it, the wider our design space becomes. Our design space in the sense of faster, better, cheaper. We can get more and more efficiencies over time, provided that we do things mindfully. So how do we do that? So if you think about what top-down design is, if you were going to go design something at school or a small project, you basically come up with a problem that you need to solve. Absolutely nothing wrong with top-down design. You break it down into sub-pieces and sub-pieces and so on and so forth and whatever, and then you get to something that you can actually write code for, and then you write the code and you test and integrate it bottom up. You build, design, and test, or you build it, test it, and integrate it bottom up. The problem is that in the large, this creates an exponentially large number of leaf nodes. And that is a problem for any large organization. And it, obviously, if you didn't have to have an exponentially large number of leaf nodes, that would be a huge benefit just from a maintenance point of view, never mind a development point of view. So application software is typically top-down, collaborative, and malleable. Library software is typically bottom-up, reusable, and stable. They're 2 very different branches of development. And in fact, the kind of people that do top-down design and the kind of people that do bottom-up design are 2 relatively different kinds of programmers. And what they are attempting to do is really a different set of goals. The application developer is solving a business problem. The library developer is solving a variety of problems, none of which is specific to any particular business need. All of them add business value. So again, these are very different disciplines. If you take a complex application, it's typical that it'll have a complex boundary that's moving all the time. So to try to specify a complex application is not only difficult, it's a moving target. The wonderful thing is that within the application, there are many regular pieces that recur and will recur in the future. If you can identify those regular pieces, such as a standard component, then you can take advantage of it now and in the future. There are many standard components in typical applications. There are also bigger components that might recur. And you can see here as they get larger and larger, something like this might be a very large reusable component. Perhaps it's an entire database system, or perhaps it's an entire ticker plant, or some large piece that's used widely throughout the enterprise. It's a reusable piece. It's not what you would typically think of as reuse. You might even think of it as use. But the point is, it appears referenced from many different applications. And so in that sense, it is reused. Used or reused, it appears in many applications. So if you're repeating code in many applications, you get a picture that looks kind of like that. If you're capturing that bulk of the code in library software, then each application has less code to write, and that means we're better off for it. This is a good idea. So if you think of something simple like a circle might be representative of some piece of software that we want to build. If we divide that software in sort of arbitrary ways, we get something that I like to think of the cracked plate metaphor, where the individual pieces aren't useful in any way other than where they were originally created. Another way to think about this is, imagine if your mother says, go downstairs, brush your teeth, and make toast. And you say, aha, I'm going to build a toaster toothbrush for that purpose. This is not a factored piece of software. It's not a factored piece of software. This is actually just a big pile of stuff that somebody glued together and serves one function. So these are two different metaphors for what we're talking about. Now imagine we have something that's a little bit better. We'll call this collaborative software. The dependencies across collaborative pieces in a system are not as tightly coupled as they are in a brittle, broken plate metaphor, but they are clearly aware of each other. And so those pieces are not invented independently. Another analogy would be a toaster with a hook and a toothbrush with a hole. And you can imagine, yeah, that makes sense in some context, but who would buy a toaster with a hook or a toothbrush with a hole separately? That doesn't really make sense. So these are not really reusable pieces. These are collaborative pieces. So brittle pieces are usable within one version of one application. Collaborative pieces are usable across many versions of the same application, because from one version to the next, the basic design doesn't change that much. But what we're really looking for is to have many versions of many applications share the same software. That's the kind of reusable software we'd like to have. So consider that a piece of reusable software is easy to explain, and it can be built up in terms of other reusable pieces of software that are themselves easy to explain. So for example, a gray square, a black a triangle, a light gray rectangle, or a clear semicircle are things that are fairly easy to explain to somebody in words. And what we'd like to say is that they have a small surface to volume ratio, which means that the interface is small and easy to understand, whereas what is done for you is proportionally large and useful. The most reused things have that property. So if we had a toaster and a toothbrush that were themselves independently useful, and then we had something that could connect them, such as an adapter, then we'd get something like the glue that can take all the software, the reusable pieces, put them together into another reusable piece. We also get the toaster and the toothbrush and the adapter and the glue independently. So this is a good thing. Let's imagine we have a big monolithic block of software. This is typical of some large behemoths that one might have if we didn't have any sort of strategy for developing large legacy software. Now, if you think about what we could do, there's a fellow named Dijkstra, and he invented this notion of physical hierarchy within systems, small pieces that are built and tested in place and stacked like bricks. And even though their interfaces might not be all that pretty, when they're stacked and tested this way, they can be very reliable. He claimed along the lines of even mathematical proofs. Many mathematicians would disagree, but as we all know, mathematicians prove things, and they're human, and humans make mistakes. And having a program go through and mechanically verify what you wanted to prove is a very, very valuable tool. This can be done either at runtime through unit tests or through static analysis or both. There's all kinds of ways to help humans do a better job than humans do naturally. There's another fellow named Parnas, and he said that modular code was what was important regardless of its physical structure. And so if you make a change to the internals of a module, the surrounding modules are not affected. Both of these ideas are very important to what we do. And if you add to that thorough interface documentation within the boundaries of a system, you pretty much get what we call a component in our methodology. So if we take a big monolithic blob of software and break it down into coarse levels, well, that's better, but that's not good enough. If we make them finer levels, still, if they span each other, we still don't have the kind of independent reusability that we want to have from any particular node in the physical hierarchy. If we were to do what we call silos, there's a lot of advantage to that because the people in the different silos can work independently and they're not encumbered by what other people do. The problem with this is that the bottom of each silo repeats a lot of the code that we would naturally want to use. So the solution here is something that looks like this: finely graduated granular software. And at each level in the physical hierarchy, we drop down a level of abstraction. But any single piece in that physical hierarchy is stable and therefore available for independent reuse, either by other software components or by application components. I cannot emphasize enough how important this is. This slide, number 19, is what we are aiming for. All right. So in other words, we're taking a piece of software and breaking it down into subcomponents and sub-subcomponents and so on and so forth. If you imagine the toaster toothbrush has a toaster, a toothbrush, and an adapter. And each one of those is broken down into its subparts. As you can see, a case and a chassis, a handle and bristles, an arm and a joint, and so on and so forth until you get down to something that can be implemented independently, some sort of atomic piece that doesn't make sense to further decompose. And you'd be surprised how far that goes down. And by the way, those things do reconverge. At the very bottom, you'll find there aren't that many pieces that you need. At the very bottom, there are a few very fundamental pieces that are reused very, very many times throughout your software system. So now let's take a look of exploiting what we'll call finely factored library software. So classical reuse, we would create a flashlight, and we create for a toaster flashlight. And the flashlight would have to have sub-implementations of lens and stock. But what we're doing is we're reusing the toaster and the adapter in their entirety, and then we're creating another piece to create the toaster flashlight. That is what reuse is. Now let's look at the difference between that, which is just reusing two other pieces and adding a third, and hierarchical reuse, where what we're going to do now is we're going to add a scrub brush, but now the scrub brush itself is using the sub pieces that were already available within the system. So this is the fundamental difference between just plain old reuse and hierarchical reuse. The scrub brush itself is using a subpart of something that was already there. Imagine we have a function. If you have a function of 6 elements, most likely there'll be 7 or 8 someday. If that function happened to be implemented in terms of other things that were individual functions, then when the time comes to extend this function without changing it, we can add those other sub-functions, and then we can reuse those pieces independently. Again, we have an example of hierarchical reuse. Imagine we have a proxy and a server and a client. What if we want to upgrade our transport? How are we going to do that? Suppose we want to go from one version of HTTP to another. What would we do? We'll see an answer to this at the very end of the talk. Let's look at some sort of software that's stable and we want to extend it. One way to do that is to add a member function to the container or whatever. But as we know, that violates a very important property of stability. We don't want to go in and muck with things that are stable. So what we do is we create a free function. Typically, this would be as a static method of a struct, but that's another story. And then we would use iterators to iterate over the pieces of the container. And by doing that, we don't have to add a private method to the container. We can simply extend it without having to change it. This is a principle known as the open close principle. Another example is we want to do some sort of fancy print. Instead of writing a new print method for the container, we create some independent function that the client could do in their own code, for example. Then again, we use iterators to extend without modifying the library software. This is a very important principle of what we need to do and how we design our software. We want it to be extended without being modified. Open, closed, open to extension, closed to source code modification. Now imagine we have a system like this where we have a PostScript printer and we have a PostScript output device driver, and then we have some account report writer. So this is typical. These physical arrows are not inheritance. They're physical dependency. And I emphasize the physicalness by the three-dimensional thing that is an actual physical device. Physical design is an important part of what we do. It's complement to logical design. And we didn't talk about it a lot in this talk, but please suffice it to say that it's critically important. This is the depends on relationship. It's a physical dependency. This is also a physical dependency. Here we have a diagram that shows how each of these pieces are built out of fine-grained modular library software. In other words, we're hierarchically reusing this other software. This is a well-factored system. Now imagine we want to extend to different kinds of printers. One way that's typically done, and is of course not a good idea, is cut and paste reuse. We do not want to cut and paste. We would much prefer to reuse things in place. So instead of doing that, we might think to create a single module that unites all of the three different devices and call it a device manager. Now look at this for a second. There's definitely something that is wrong with this, and that is we're taking something that might not ever be part of a single executable and requiring a dependency on three different things. This is not something that I'm excited about even considering, because it's putting gratuitous dependencies where none are needed. One of the things we strive for is to make sure that we don't create dependencies on things that we won't need. So this is another design principle that's just so natural to me that even to mention it, of course, I have trouble even thinking. But in any event, we're not going to do this. What we're going to do instead is something that was first talked about, dependency inversion, by Uncle Bob Martin in a book that predates my 1996 book, only one that talks about this dependency inversion that I'm aware of, or physical design in general, in terms of C++. And so we now have an output device, which is an abstract interface. And then we have implementations, and the implementations are ISA and no. Object-oriented programming is not the evil that might be claimed to be. Once upon a time, it was the greatest thing in the world. Then it was decided it was the worst thing in the world. Well, it's neither the greatest nor the worst. It's part of our toolbox. For large-scale design, it's essential. And then we have clients that make use of the output device in their interface. That little white bubble, we'll talk about that in a moment, is users in the interface. So ISA and users in the interface are logical relationships that imply physical dependencies. This is something that was discussed in my first book and is certainly discussed in the one we're talking about now. These are depends on relationships, and they are independent of the logical nature in which the dependency occurs. This is a well-factored software system. One thing we want to say is, if you have one client that's dictating what software does, then that software can change because no one else is affected. It's not unlike the notion of something that's movable. If you can change it, if only one person cares, then that's fine. But if multiple people are referencing the same software and you try to change it, other people could be adversely affected. So by definition, software that is reusable, is depended on by many clients, is stable. And in fact, one of the measures of stability is how many clients use it. Too many clients use it and you change it, people will come after you with pitchforks. So don't change it. This scenario where you have multiple clients telling you what to do can lead to something that's usable effectively by no one. And we call it the flattened green toaster toothbrush with flag. By the way, I want to mention I'm going to stop for questions at an appropriate point. So unless there's something that's very important, I'm just going to keep going. Then I'll go back and see if I can answer some questions. So what is physical design? These are some definitions. The arrangement of source code within files and files within libraries. There's another one. Two deliberately partition source code among files and files among libraries in a way that makes good sense, good engineering sense. So one of the things that we take as a given is that a component consists of a header file and almost always one like name.cpp file. I say almost always because in very rare situations in embedded code, you might have physical properties, but we won't go into that. So for the purposes of this talk, a component is a .h and a .cpp file. This is the header. This is the implementation. The header is the physical interface. The implementation is the physical implementation. But as we all know, a lot of the logical implementation these days with templates and inline functions and blah, blah, blah reside in the header. We also have something that is not part of the component proper, but is part of every component we write, and that is a component level test driver. This is something that's discussed in volume 3 of this 3-volume set, and it's not part of this talk. Now we'll take a look at how we lay out a component in source code. And I'm putting this here. I don't want you necessarily to read it. I'm just going over the big categories. Please don't feel like it's essential to see this. It's more of a picture. We start out with the name of the file at the top so we know what we're looking at. We're not going to talk about packages for now. That's a higher level grouping. And our definition of package and the standards definition of package are not the same. They're different ideas. They are definitely related, but a package in the standard is probably more closely aligned with what we call a component. So we have helper stuff like a stack. In this case, we have a stack const iterator. We have free operators that operate on the stack const iterator. We have the flagship class, which is the stack itself, the data members, the public interface that starts out with public types, then creators, which are the constructors and destructors, the manipulators, which are the functions that mutate the state of the object, and they simply are defined by not having a const, and the accessors are defined by having a const. If this looks like a weird way to represent things to you, I cannot tell you how valuable it is to have this kind of partition, because every single object that's constructible has constructors, manipulators, and accessors, and you know exactly what they are because they're not opinions, they're facts. So just by virtue of the fact that it's a const, you know where to find it. Anyway, that's our organization. And then, of course, we have the free operators. And for reasons that are not capricious, operator double equals and not equals and all of those kinds of operators are not methods of a class to provide symmetry with respect to the left and right side user-defined conversions. All right, among other reasons. And here's the end of that file. So if we were to look at this as a diagram, we have 3 kinds of things in a logical diagram. We have uses in the interface, which means a function uses a type in its interface if the function names the type in its signature as part of its return type, and a type uses a type in its interface. A class, for example, if any of its member functions use that type in the interface. So this is uses in the interface, means it's programmatically known to be part of the usage model. Uses in the implementation means it's used substantively, but there's no programmatic way to get your hands on the thing that's being used. So uses in the implementation in our notation implies that it's not used in the interface. If something's used in the interface, it's used in the implementation. Something is used in the implementation, it implies that it's not used in the interface. This other thing, every .h is included by its corresponding .cpp as the first substantive line of code. They're 4 properties of a component. We're not going to talk about them here, but they're definitely important properties that make a .h.cpp pair more than just that. The physical interface, again, is the header file. The physical implementation is the CPP file. Now, not every component is considered created equal. Some are very simple. For example, they have just one class, and more complex ones have maybe more than one class. Yet another component might have several different classes in it, but all of them are tightly related. And typically the reason for having more than one class in a component is friendship, not cyclic dependency, not anything else. Friendship is really the reason why we would do such a thing. And then finally, we might have something that's extremely complex. We'll call this more like a facade. And a facade is not something that can clearly be completely implemented within one class. It's going to delegate to other components. It can be implemented in one component. It can be delegated to other components. So if we take a look at some sort of physical structure, the structure might consist of very simple things. It might consist of more complex things or very complex things. I'm showing this more as a pedagogical example. Whether you'd have a particular body of code that has a point and a matching engine, which is something that's used to pair people who want to buy stocks and sell stocks in the same program, who knows? The point might be part of a graphical interface. The iterator might be something that's used to do some low-level thing that has nothing to do with the application itself, but in the full dependency, that might happen. So here's a point, very simple at the bottom of the physical hierarchy. Here's a container class. It might be a little bit higher than the most simple thing. And here we are way up the chain in some sort of application level library that's creating what's called a matching engine, a very complex piece of machinery that's reused as such throughout a large company like, I don't know, a trading company, or who knows, maybe Bloomberg. I'm going to take a quick pause for questions now and just see if there's anything that I need to answer real quick. So let me just look and see if there's anything. If it's not something so, gosh, okay. I was asked if the business has a large culture of developing monolithic from scratch applications, how can you convince them that a reusable library framework has business value? So this is an excellent question. Show them this talk, have them read this book, and have them relive my life for the past 20 years. I had to do exactly that. It turns out that this is a long-term investment. What you need is somebody who's either high enough in the company and plans to be there for a while that what happens 3 years from now actually matters, or you have to develop a sort of a groundswell of leaf level people who together decide to do this. I'm not going to say it's easy, but it's sort of a question of having to have the mindset and the will to make it happen. I don't have a good recipe for it, but persistence is a good one. If you go to a new company, the best thing you can do is put your head down and make yourself useful. Then over time, people will see that you're useful. Then you go to the next step, which is you say, here, I think this. And if people don't agree, you say, okay, then they find out you were right. And over time, if you play your cards right, people will actually listen to you. And when they finally listen to you, hopefully it doesn't take 20 years, then you can tell them this is a good idea. In any event, if you're a team lead, you don't need permission on how to organize your team's code. Just do it. And finally, the way to separate that out, I think, is to make sure that you, if you have a clean code base, try not to depend directly on something that's quicksand. Try to build your code separately and have them depend on you. That's what I did. I'm going to take some of these other questions later because I'm low on time, but I think that question definitely deserved some attention now. So now I'm going to go on to the next step, which is to talk about an analogy. So top-down software design is a recursive partitioning problem, and it's a hard problem. And attempting to optimize it is a complex, is satisfying a complex cost function. So we're going to create an analogy between hierarchical software design, which is hard, and something that's not as hard and quantifiable. So take a look at this. We have this text here. Suppose that we want to write a program to format function documentation that avoids leaving lots of space at the end of a line due to very long words like my very long type. Maybe you've done this and you say, gee, I wish that the ragged documentation under the function looked a little better. We don't like this. We don't even like this. What might we do? Well, we'd like it to look a little bit more like this. But somebody might say, well, how can you optimize, how can you automate that so that it looks like that by just applying some sort of editor function to do it? And so that you get this nice, more even spacing at the end. So now what I'm going to ask you to do is look at these two things. How would you write a program that optimizes the layout of each line so that the spacing is more even? Think about this for a second. What would you do? So what you want to do is you want to create, for a series of words, you've got these words, you want to partition the words somehow such that some function of the spacing at the end of the lines is minimized. And that function is any nonlinear function, any superlinear function like x squared, x cubed, x to the fourth, because a long gap will be treated much more harshly than two medium gaps. And you'll see that done right here. This is a cost function. Here we're going to see the cost function in action. So here on the left side, you see I have used a greedy algorithm to fill in 3 words. Over here, you've seen that I've wisely chosen using a global algorithm not to fill in 3 words. As a result, the first 2 lines contribute a lower cost to the overall cost function. You see 1 cubed plus 9 cubed is less than 5 cubed plus 5 cubed. You see that? 1 cubed and 9 cubed? You see the 5 cubed and 5 cubed? When you add them up, you get this. This is the cost function, and the cost function is lower on the right because the sum of the cubes of the number of trailing spaces on the right is lower. Better partition. Okay, so what we're doing is we have a global cost function instead of a local approach, a local algorithm called a greedy algorithm. So it looks better, and the same would be true if we had a global cost function that optimized hierarchical design. That would be wonderful. But how do we do that? So anyway, we're going to describe a programmatic solution to the problem that we do understand, which is how do we optimize the rendering of text so as to make it less ragged. And what you see here is a library component, and the function, the struct format util, is the one that holds the namespace for the actual function that we're going to create. So this is the name of the header file of the component. This is the struct that holds the namespace for the static function that is the utility function. This is the utility function. Utility function. And now we're going to look at the utility function and its contract. Here it is. Now you can read this. I'm not going to read it to you, but what you need to understand is that you have a prototype. The prototype consists of return type and a bunch of formal parameters with types. But that's not enough. You need a contract. Contracts are very important, something that we've been working on very, very aggressively at Bloomberg since 2004, almost made it into the C++ standard. And by contracts, I don't mean just the description here, but the actual ability of the compiler to help you check them. So that's what contract checking is in C++, hopefully 23. But for right now, this is the English version of the contract, which you could then apply precondition checks to somehow using some homegrown system, but hopefully soon in C++ itself. All right, so this is the top level application program. This is something that will be used to leverage the library function. So what we're saying here is the library function alone doesn't get the job done. This is the actual application program that makes use of it that an end user would call. And the whole point is that this application program is going to call that library function. So here's the application program. We're specifying the nonlinear function as we said, and it's just going to be the number cubed. And then we're going to invoke, this is a local function. This is one of those malleable functions that's part of the application. And then finally, we've got the main program, and the main program is going to call the library function. So this is where we call the library function, and all we do is we set up the call to the library function. The library function does its work, returning the partition that we need as the first argument, at which we're passing in by address, and we're done. This is where we print the results. Now we're really done. Okay, so what's the pseudocode for the library function that we're trying to create? The pseudocode looks something like this. We're going to say if a particular sequence of words fits on a line, great. If it doesn't fit on the line, which is a parameter to the function, then we're going to partition it every way we can by dividing it in every possible partition pair, solve the problem recursively, and then take the pair that has the least sum cost and return that as the answer to the question. So this is the, if it's good, leave it. If it's not, recursively partition it, and then load the result. So this is the library component implementation file. Now, I'm showing you this not because I want you to understand every part of it, but just simply so that you have it on the camera. You can go back and look at it. This is the name of the file. We always do that. This is the local context that we're passing in. This is the recursive subroutine that we're going to call from the main subroutine, which is the entry point to the utility. And I'm going on with that. And this is the main entry point to the utility. Now, again, I'm not asking you to read this. I just want you to know that this is how much code it is. It fits on a few slides. You can go back and look at the slides. It's also in the book. In fact, every picture here is a figure from the book, so you don't have any question. If you want to go back and read about this, chapter 0 is exactly your friend. It's explained all thoroughly, totally, utterly in the book. So where we have a recursive descent approach, we're going down and looking at each thing, but there are an exponential number of things we have to look at. And while this program works in theory, it doesn't work in practice. It doesn't scale. But there aren't an exponential number of subproblems to solve, which is an important point of this whole discussion. There are only a polynomial number. Why is that? Because every partition that you might want to describe for n words can be described as its starting index I, which is between 0 and n, and its final index, which is between 0 and n. So if you choose them independently, you would get n by n, which is n squared. There are only n squared subproblems. Therefore, an exponential number of calculations is a bad idea. Notice the analogy with software. If there are only a polynomial number of things to write and you find yourself writing an exponential number of things, something's wrong. We'll get to that. So given that there are only n squared problems, what can we do? And you'll see the analogy is we don't solve them over and over again. So what we're going to do is we're going to add what we'll call a solution cache. And if the problem is already in the solution cache, we use it like a library. And if it's not, we write it and put it in the library. So what does that look like? I'm showing you the same code as before, except I've taken away anything. I've added code to what we had before, which is very important. It's an additive process. So I've added the solution cache. I've added a data member. I've added the part where we look to check to see if there's something there. And then I've added the part where we say if it wasn't there, I calculate it and I put it back. That's all this is. That's called memoization or dynamic programming. The point is you don't do a calculation twice. Once it's done, you save the results. Now you eliminate the vast majority of the work. So when you go to run this, if you look at the number of potential subproblems versus the actual number of unique subproblems, it becomes clear that one of them is scalable and one of them is not. So let's take a look at the implementation. The way we did this problem was we created a map of subranges, and every partition was copied into a new vector as a sequence of indices. And you'll notice that those indices were copied, not referenced, when we went to larger and larger partitions. That copying is akin to cut and paste. We don't want to copy paste. It would be much better if each individual partition referenced the top level solution, which is decomposed into sub-solutions and so on and so forth hierarchically, where each sub-solution had finite size. A node, much like a component, has a finite size, which is typically that can be tested by a single test driver file. This is by reference, not by value. So in other words, instead of copy-paste, we reference the library component. Fixed size nodes, much like a component, it's not arbitrarily large. What about this map? Well, a map in C++ is a balanced binary tree. It's required to be that way because of the properties being able for it to be ordered and certain other properties of guaranteed logarithmic worst case time. But if we don't care about that balanced tree, we might decide to go with, let's say, an unordered map, which is a hash table based thing. And that has different properties, and those properties are typically faster than what we would achieve with the tree. But guess what? We know that there are exactly a triangular matrix of solutions. So we can create that triangular matrix in terms of a triangular array, and we can pre-allocate that space as compactly as possible. Moreover, we can know exactly where to go without having to do any sort of expensive or possibly non-constant lookup. So the packed array is the winner by far. Now, beating the analogy to death, the original solution was intractable because we had to do an exponential number of calculations. We then said we're going to create a library, but we're going to copy paste the solutions. That's the by value solution. Then we said we're going to not do that. We're going to do those solutions by reference. That's the hierarchically reusable library. And then finally, the carefully curated library is the one that has many easy ways to find what you need. Now, I know I'm stretching the analogy, but I wanted to show you that the more time you put into thinking about this, the better your software development can be. And so this is my analogy. Let's just beat it one more little bit and say, what is the analogy? So you have a subjective cost function in software development. What does it mean? Is it easy to read? Is it easy to use? Is it efficient? Is it whatever? Is it interoperable? In text partitioning, we have an objective cost function. Application programs and suites of programs, those are related to the entire text and the entire text again. Those are the clients, if you will. That's the end product. Factored design, partitioning, logical content, words. Leaf component is a line. You're trying to put logical content in a physical entity. What is a component? A component is a solution. It might be a sub-solution. It might be a sub-sub-solution. Hierarchically reusable library is a solution cache. An enterprise-wide, globally accessible. To optimize an enterprise-wide library is to do a global optimization. Source code copy and paste, independent solution copies. That means that I'm giving you the indices for a partition in this problem. I'm giving it to you as a complete vector, not as pointers to two subvectors. Software packaging strategy, curated components. Again, this is a well-organized solution cache, possibly having a triangular matrix where you can find things instantly. Finding things in a library is a big issue as well, of course, so you have to keep that in mind. Uniform component size. This is the uniform node in that solution where you're not copying things. That means that you're referring to other things, and so the space utilization in your program goes down. Reusable software is stable. By the way, once you calculate an answer, it never changes. So everybody that depends on that answer never has to worry about being broken. Again, it's an important point. Component dependency, reference to subroutines. So if you have a component that depends on two sub-solutions that are components, a reference to a solution depends on other solutions, same idea. Finding a relevant component is the same as finding a solution quickly in the solution cache. So that's the end of the analogy. And let me just see if I can take, I'll try to look for another question. I apologize that I'm going so quickly here, but I did want to get this all in. So let me see if I can answer another question. It says, you mentioned vocabulary types a lot in the book, but explain them in detail in later volumes. Can you briefly explain what they are, especially in the context of software capital? I will. That's an important question. I wish I could answer more now, but I'll answer that one. A vocabulary type, very simply, is a type that's used widely in the interface of functions. If you have something that's a function, just a function, a free function, or a function as a member of a struct, you could have 17 different functions. They're not part of your vocabulary, they're implementation details. You don't have to pass them around. But now imagine you have something like a date class, and that date class is used widely throughout your entire organization. If you make a change to that date class and try to move it to some other package, or try to call it another namespace, or call it something else, it will become non-interoperable with everything else that was using it. So changing a vocabulary type is a major problem. But if it's not a vocabulary type, then it's easy to change, because you change it, you can have the non-vocabulary types, such as a utility struct, or something that's not used in the interface. Like, for example, a scoped guard. Scoped guards are not used in the interface. You could have 17 scoped guards and no one would care. But if you have, for example, an abstract allocator interface, if that is ever more than exactly one, you lose interoperability. And that's why it's so important that an abstract type in the interface must be standard, at least throughout your organization, if not in the standard itself. I hope that answers that question, and I'll try to get back to more questions if I have time after this. So let me continue. Bear with me while I get to the point here. Okay. All right. So when we're trying to design something in industry, particularly in the financial sector, the faster you get something to market, the more valuable it is. If you wait and you make it perfect, somebody else will get it there and they will get a larger profit margin because they got it there first. Over time, these products will decay to steady state and you'll get just the free, sort of the free market value. And so it's often said that there's never enough time to do it right. There's always enough time to do it over. And as crazy as that sounds, it's absolutely true. You could imagine two teams, the fast team and the right team. The fast team gets it there quickly and the right team gets it there permanently. And that's not wrong. So you might think one way to have the fast team or the right team get it there faster is to just pile on more effort all at once. And we know that that's not true from the Mythical Man Month, right? Fred Brooks would not agree. The actual staffing profile, and one that we use in my group and hopefully everybody would consider as being a reasonable one, is you start out with the germ of an idea and you move it to a real idea and you get feedback. And at some point you widen your audience to more and more feedback until it gets to a point where it's ready to put into real development. We call that a hump project, and that's an example of this curve where we've reached the part of the project where we know what we're doing, and now it's a question of execution. There comes a point where we've done most of that. The testing is not delivering too many defects, and we say we're about ready to release. That doesn't mean that we're done, because once we release, of course, there's going to be more defects found in the field, sadly. And so if there are no defects found in the field, we release too late. And if there are too many defects in the field, we release too early. So again, this is a precise definition of what we mean by delivery date, but you get the idea. So we can't do that. So what is software capital? Well, its charter is to reduce time to market for future applications and products. That's its charter. Its secondary benefit is just not to have to keep maintaining everything and reinventing the wheel. But anyway, what is software capital? It's easy to understand. It's easy to use. That's easy to say. It's high performing. And in particular, if we ever design something that isn't high performing, there'll be somewhere out there that'll want to rewrite it. And so it has to be so high performing that no one in their right mind would waste their time trying to write something that's more high performing. This has been part of our methodology from the start, that we cannot put something out there that's okay in performance. It has to be the best. Portable. We want to write things that if a new architecture comes along that's conforming to what the standard defines, that we will be able to port our software to it instantly. And so we do lots of things to make sure that we don't go outside the standard and create platform adapters and such, of course, without losing efficiency. And finally, reliable. And we really do strive to make our components as reliable as the compilers themselves. And if that sounds like it's not reasonable, believe me, it is reasonable. The reason compilers are pretty good is because they're field tested by a lot of people, but it is not only because they're unit tested. It is quite surprising how many little corner defects in the various compilers exist out there, and they do get refined over time, and there are defect reports. So compilers are usually right. And if it's a question between your code that you just wrote and a compiler, chances are real good it's your code. We want our code to be at that level by the time we release it. We have test methodologies that are described in part 3 of my book that come close to doing that. When it's finally released, it'll be quite something, I hope. Anyway, continuing, imagine you're in one of those home improvement centers like a Home Depot or a Lowe's. And in this home improvement center, all of the things in the first row, the simple things like the nails and the screws, are the piece parts that the things in row 2 are built out of, such as let's say we had a toaster, toothbrush, who knows, a small box, a jewelry box. In row 3, maybe have pre-assembled furniture. Maybe in 4, we have pre-assembled homes. I don't know, a car. The point being that in this particular theoretical home improvement store, all of the parts in the higher level rows are implemented in terms of the parts in the lower level rows. Think of these parts as types of parts rather than actual objects, and it'll make more sense. Now, if we ever talk about any one particular one, we can see that that one depends on some subset of the other parts in the repository. And if we want to visualize that, it would look like this. And that's why visualization tools that are reflective of both physical and logical design are so important. We are actually actively researching such tools that will be consistent with what we're talking about in the book. Hopefully that will be available in the coming year, I don't know. But at some point, hopefully not too long from now, we can make this more widely available, but we're researching it now. And it's incredibly important for understanding large systems. So the idea is we started out with this faster, better, cheaper design space. And not only did we move it out so that you could make things more faster, more better, and more cheaper, we actually moved it off the axes, because built into the reuse is the speed, the quality, and the cost savings, because you don't have to reinvent the software each time, test it each time, and inventing and creating it does take time, it takes energy, and it adds the risk of adding bugs. And of course, it adds maintenance cost. So if we did this over time, we'd see that we would, without software capital, we would see that we would gain experience, but we would lose productivity due to the cost of ownership, because we didn't organize things just so. And this curve is flattering to the people who chose not to use our methodology. It's actually much worse than that. If, on the other hand, we took a small group of people, as we did 20 years ago at Bloomberg, and moved them to a group known as BDE, which I was the first person to be part of, since I was the one that created it. After some period of time, T1, some productivity was seen. And after some period of time, T2, the productivity, cumulative productivity, past the point where if we hadn't done that. That was many, 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 many years ago, and we haven't looked back. So here we are almost 20 years hence, and we're saying that T1 might have been on the order of a year or two. I can't exactly say where T2 was, but it wasn't that far after T1, I can assure you of that. And then after that, here we are. This is the critical point. This is the break-even point for doing this. If you ask me what that time is, I'm sure if I had it to do over, I could have done it faster. But whatever time it is, it's kind of like, well, how much time do you want to have before you've saved enough for your retirement? You want to make that as soon as possible. And if you're smart about it, you'll do it sooner. You'll start sooner. What can I say? Once you've passed that point, there's no looking back. All right, so you start with an application. There is no software capital. So you create some. That application can then either choose to use that new software capital in the next version or not. But the next application that comes along can start using that. If it does, less work was done. You can then extract software capital from that. That doesn't mean copy and paste it. That means rework it and assimilate it by a different group into your software capital repository, which of course is hierarchical reusable. And then that could retool. But then now when application 3 comes along, you have a substantial body of software to draw from, and you've made a substantial saving. So the point is, the first application does not benefit. The second application benefits slightly, but the fifth application benefits tremendously. And I don't need to tell you what the 175th application does. Now imagine you come along, and we talked about this early on with, say we had an HTTP protocol, and we wanted to upgrade it. Well, we're not going to go in, let's say that's you, we're not going to go in and change it and break everybody else in our system. What we're going to do is, we're not going to copy the system either. We're going to take those pieces that are dependent on that, and we're going to fork them. But we're going to fork them in the way where they can coexist. So you have those solutions and those solutions prime. And it was asked earlier, can you do that with vocabulary types? No, you can't, which is why this becomes a real engineering problem and why vocabulary types are so important. But assuming it's not a vocabulary type, then yes, you can, and this is the way to do it. Drawing this picture in ASCII was hard, but it's possible. I did draw it in ASCII in my book when I did the original draft. This is how we would do the HTTP upgrade, by the way. We would have HTTP 1 and HTTP 2 coexist. So here's a system that you might reuse. It's embedded in a much larger body of code that is interoperable, that follows the same design rules that we have that are described in the book. The long-term vision in this picture was literally drawn 20 years ago with what we have now as being the vision. This is what we aspire to, where most of our code is library code and the rest is app code. Without it, we get something that looks like this. So the end goal is to have software capital that per component is enormously expensive. And it doesn't matter, because without it, what would have come is code that is very, very duplicative, and the maintenance cost would be prohibitive. And so the value of the software capital far, far exceeds its cost, because it can be reused across an unbounded number of versions of an unbounded number of applications in your domain. I have to emphasize this. The standard is not software capital. It is not domain specific. The software capital is what you have invented because you invented it for your own purposes. If you follow this methodology, it's really useful. Somebody else's software capital is not your software capital, especially if they don't follow the same methodology. So one of the reasons it's okay for us to open source our software capital, and that it's not a competitive advantage that we want to keep secret, is that we actually feel that this software capital, being stable and whatever, will entice people to want to come work at Bloomberg, because our methodology is, this is our methodology, which started 20 years ago. And with hindsight, we did the right thing, and we're going to keep doing it. And my advice to anybody who's has any say in anything that they're doing, please consider using this methodology, because you won't be disappointed. Kind of like a good stock tip, which I won't give you here. And that is the end of the talk. And I have a couple of questions accumulated. So what I'm going to try to do is answer a couple of them on this talk, if I can. And then I will, and what I'm trying to do now is figure out how to get my mouse to the point where I can scroll to look at the questions. So bear with me a second. Okay. So suggesting great resources and books. I want to tell you that a fellow friend, colleague of mine, Vittorio Romero, and I are working on a book to explain in practice. It's called Embracing Modern C++ Safely. And this would be a great book to learn about how to use 11 and 14 features with 7 years of hindsight, how to use them in a way that's consistent with the methodologies described in this book. Another one would be, as far as architecture, there's no book that I can possibly recommend other than my own. There are other ones out there. Unfortunately, and I'm not saying they're not good, unfortunately, over the last year and a half, I haven't had a chance to read some of them that might be totally awesome. So I'm not going to recommend an architecture book other than the one I'm suggesting here, but please don't take that to mean that they don't exist. And I tend to feel that there's a lot of kindred spiritship between me and Uncle Bob. So if you see anything by Robert Martin, I would gravitate to that. Is your experience with what's best a way to build reusable components? Design them up front as part of a process to build applications, or factor them out of applications as reuse seems valuable? Awesome question. It's a matter of both. It's kind of like, do you do test-driven development? I mean, the idea is, once you know, like when I started at Bloomberg, I knew from my experience what I would need before I could even look at an application. I couldn't design a piece part of an application until I had the piece parts that I could use to build those piece parts. And even those piece parts needed piece parts, and so on and so forth, below and below and below. So I had to do that. And the answer is, you got to start from first principles. And if you don't, you need somebody who at least knows what vanilla software looks like, and you need to write the reusable software to build the vanilla software before you build the application software. Once you see application software in the wild, obviously you want to see 2 or 3 uses of what appears to be the same thing, and then you want to say, yes, I want to pare that down to the intersection, not the union, the intersection of those things. Be 80% of every use. Don't be 100% of all three uses, because you'll wind up with what we call a Winnebago class or component that's not usable by anyone. The flat and green toaster toothbrush with flag thing. Don't do that. So listen, I'm out of time. I'm going to answer one more question, I guess, and then I'm going to maybe somehow figure out how to be available. Do you think popular SOA service-oriented architectures fit in finely graduated granular software architecture? So my parting answer here is going to be, that is a different level. Just like you can have a binding like JavaScript to a language like C++, the JavaScript level depends on the C++ level, and the software-oriented architecture level is a bunch of services that are built out of reusable pieces. So if you think of an SOA as an app, and you have 10 not an SOA, an SOA entity. So you have a service. Think of each service as being an application that provides a service. All of those services could use the same software capital code base. The nice thing about SOAs is the software capital doesn't have to all be in the same language. You could have a code base in Java, you could have a code base in JavaScript, you could have a code base in C++, and the services interact regardless. So that's my answer to that. And with that, I'm going to thank everybody for coming to my talk, and I'm going to find out from my buddy Kevin how I can go answer more questions. And if you want to find me and send me email, you can find me in my email in the standards committee, because every paper that I've submitted has my email on it. You can send it to my work email. So if that's what you want to do and you have a question, I'll try to answer it. Hopefully I'll get my book out and still answer all your questions. So thanks again for coming, and I guess I'm done.